Hi folks, welcome to lesson 3 on partial fractions. Okay, so before we can get into improper partial fractions, we need a little reminder on algebraic division. So let's just have a recap there. We previously have divided algebra using the grid method. Here's a reminder of how it works. So if we want to divide a large polynomial by a small polynomial, we first place our division polynomial on the top of our actual grid. The next thing that we need to do is we need to take the biggest term in our polynomial and put it in the top left corner. And from then we're essentially filling in the gaps. So if we had x times something to give x cubed, that must be an x squared that goes on the left there. If we've got an x squared here and we've got a 2 and there's a missing square, we must fill that in with a 2x squared. We then think, well, we don't need 2x squared. According to our actual question here, we need 1x squared. So that means we'll need to subtract 1x squared from that to make it happen. If that's a minus x squared, then that's something times x, then that must be minus x. And the process repeats and repeats and repeats until we end up with the whole grid sort of filled in. And we can get from the left-hand side here that essentially your answer is x squared minus x plus 6 with a remainder. Now for the remainder, we need to look at what we didn't actually cover. So according to this, we should have had 4x, which we do. That's great. And we should also have minus 3, which we don't. We've got plus 12. So to deal with that, we need to take away 15 and have that as our remainder. So we'd end up overall with x squared minus x plus 6, which we read off from the side, and then a minus 15 remainder over our original fraction of x plus 2. Okay, here's a slightly more in-depth method. So I'd like you to try this first. Here's the general grid that you'd want to use. And we'll have a look at the answer now. So we should have ended up there with x squared plus 3x plus 1 on the left hand side. And then the remainder is going to consist of two parts. We want to get 2x here, but we've actually got 5x. So we're going to need to subtract 3x as part of our remainder. We want to end up with minus 7, but we've got 2. So we want to subtract 9 for the other part of our remainder. And we'll end up with this combined remainder on top of x squared minus x plus 2. You can write that slightly more nicely as subtract 3x plus 9. Okay, so that's the grid method. So let's see how we can actually apply that with our partial fractions methods that we've looked at last week. Here's I would say a fairly straightforward example. We're told the form that we have to put this in, and we can see what's different this time is that we have some constant term, and we've got to work out what that is. Now you can do this using coefficients, and I'll look at that method a little bit later, but I'm going to try and stick with the grid method here. We first want to expand the base of our fraction, rather unusually for algebraic fractions, because we need to divide by it. So we'll set up a grid method and we'll work out that, yeah, that constant term is just 2. Remainder, well, we've got minus 4x and minus 16 here, but we wanted 5x and minus 3. So we'd need to have a remainder of 9x to get from the minus 4x to the 5x, and 13 to get from the minus 16 to the 3. So we can make the following conclusion. Now, we then want to take our 9x plus 13 over x plus 2x minus 4, and we want to put that in partial fractions. You've noticed here that I've kept them as b and c, rather than writing them again as a and b, just because I don't want to get confused. I'm then going to go through the same process we went through last week, so we're multiplying up by the x plus 2x minus 4, and we're substituting things in. So if I substitute in 4, I can get that c is 49 over 6. If I substitute in minus 2, I can get that b is 5 over 6. And so we'll end up with our final answer of this horrible looking fraction, 2 plus 5 6 over x plus 2 plus 49 6 over x minus 4. And do remember you can take those fractions down into the denominator to make this look slightly more pleasant. So again, let's have a look at a more heavy duty version of this question. I think this is about as complicated as you could be asked to do in maths. But again, we're going to start off with a grid method. X squared plus 6x plus 9 is on the base. 3x squared, 4x plus 1 is what we get when we do our divisions. And we're going to end up with a two-part remainder. So we've got a total of 42x there, but we want 47x. So we're going to have a remainder of 5x. And we've got a total of 9, but we want 31. So we're going to have a remainder of 22. So 5x plus 22 as our remainder. We're then going to split the 5x plus 22 into a partial fraction. And just remember, we've got a repeated root here. That x squared plus 6x plus 9 factorizes to x plus 3 squared. So we need to have a linear and quadratic version of that root as our denominators. Again, we'll multiply up by x plus 3 squared. We'll sub in minus 3 to get that e equals 7. We'll sub in 0 and e is 7 to get that d is 5. And we've got our final answer just the same as we had last time. Yeah, it's not actually that much more difficult than the previous one, it's just more algebra. So if you don't like division, there is another option, which is to compare coefficients, and I want to run through one example that uses that. Here's a question quite similar to what we had on the previous slide. We've got a quartic divided by a quadratic. We can give everything a common denominator right from the start. We can take that ax squared, that bx plus c, we can multiply it by xx minus 2 and put it over xx minus 2. We can multiply the d term by x minus 2, the e term by x, and we can end up with this identity where we've got our x to the 4 plus 2x minus 3 is equal to all of these things combined. Now, from here, you've got lots of options about how you do it. You can set up simultaneous equations. You can definitely sub in x equals 2 to get the value of e. We can definitely sub in x equals 0 to get the value of d. From then, you can compare coefficients. We can look at the x cubes, the x squared, the x to the 4s. You can expand it and compare and contrast, but I'm just going to compare things straight away. We've got x to the 4 on the left-hand side, and if we multiply the a by the x, we're just going to have ax to the 4 on the right-hand side. So we can get from that that a equals 1. If we looked at the x cubed coefficients, there are no x cubed coefficients on the left-hand side, but there are minus 2a plus b on the right-hand side. So we can get from that that b is 2, and we can do the same with our x squared and get c is 4. Gives us our overall answer, x squared plus 2x plus 4 plus your partial fractions. So yeah, that's another option. You might want to go back to the previous slides and see if you can run that with those. Now, if you're just doing maths, that's it as far as partial fractions is concerned from you. You can make a start on the work. But if you're doing further maths, you might want to watch this last slide just to go through, well, what if? So we can have a situation like this. And the problem with this is that the denominator, the x squared plus 1, does not really factorize. It obviously has a complex thing, but we're talking about real roots here. We can still run through the long division as before. We can get ourselves a remainder this time of 2x plus 4, and we can't actually do anything with this. We can't split that up. We can't make it into two fractions, so that's as far as it goes. So just be aware that you can have a situation where the denominator does not factorize, and that's fine. You just live with what it is. A slightly more complicated version of that would be something like this, where we have a given fraction that's equal to something, and we can't do a long division here because the top has a lower power than the base. So we have to go through that whole multiplying up process. We have to then substitute things in. So in this case, if we sub in 0, that'll get rid of everything except the b. And then we have to do more coefficient comparing. So we can expand that. We can look at just the coefficients of x. We can get that a is 1 from that. We can look at just the coefficients for x cubed. That'll get c as minus 1. Look at x squared. That'll give us d as 8. And we'll end up with this as our final answer. Again, that's not on the normal maths course. It is just on the further maths course. But it's probably worth being aware of at this point, that it ties into everything.